Now, I want to talk a little bit about the anatomy of the eye, because, of course, it is your eye that allows you to sense the light. It's not quite as easy as all that. Your eye is a really interesting tool that um, lets you see a very clear version of the world in front of you. Now, the eye takes advantage of a natural physical phenomenon. So let's say that we make a tent in the middle of your backyard. It's best if this tent is round, and you're going to sit inside the tent. And inside the tent is going to be perfectly pitch black. And so what I'm going to do is I'm going to cut a hole right in the tent, which will allow some light from the outside to be projected onto the opposite side. Now, once that is there, I'm going to stand in front of the tent. There I am. Look at how shiny my head is. Now, you inside, what's going to happen is that in that pitch black tent, you're going to see an image of me projected onto the back of the tent. Now, this is just a natural phenomenon. So that image isn't always perfect. If I take a step back or if I take a step forward, what's going to happen is that that image of me in the back is going to get blurry. Now, another thing you might notice is that that image of me in the back of the tent is upside down. Um, this is all happening in your eye as well. Now, you don't have a tent in your eye, but your tent or your eye has a sclera. And the sclera is kind of like the white part of your eye that gives the eye its shape. And just like that tent, in the front of the sclera, there's a hole. And that hole is your pupil. Your pupil is the little black dot in your eye. Um, Now, that allows the light to go into the eye, which is perfectly pitch black, except for the light coming in um, through the pupil. So if something were to be in front of that pupil, then it would get reflected or projected onto the back of the eye upside down. Now, I told you that if in this case, this butterfly went a little bit back or a little bit forward, the projection on the back of the eye is going to be blurry. So your eye has a few extra components to try and prevent that image from getting blurry. First of all, in front of the eye, and really all around the eye, you have the cornea. And your cornea is the clear membrane on top of your eye. If your cornea gets damaged, that's going to affect your vision, is going to mess up the light refracting into the eye, and that's going to mess up how you see. Now, you also have an iris. The iris is the colored portion of your eye. Some of our irises might be brown or black. Some of them might be blue or green or hazel. The color of it has nothing to do with vision. That's just how much pigment happens to be in your iris. But what the iris does is that it's a muscle which can either dilate to open up the pupil, make the pupil larger, or constrict to make the pupil smaller. This is important because if it's dark outside, you might want to open up the pupils to let more light in. And if it's very bright, you might want to constrict the light, or I should say, constrict the iris to let in less light into the eye. This will also help in focusing that image in the back of the retina, in the back of the eye. Now, behind the pupil, there is your lens, and your lens is just a little bag of liquid, and that bag of liquid is held in place by a bunch of muscles in your eye. if you're ever looking at something very far away and you're kind of straining your eyes to see, or if you're looking at something very close to you and you're kind of straining your eyes to focus, what you're doing is controlling those muscles. Those muscles might make the um, lens flatter, or they might bunch it up so that it's a little bit more like a lens. Um, and that will focus the light onto the back of the retina. Now, if your sclera, the shape of your eye, is not perfectly circular, if it's a little bit more elongated, or if it's a little bit too flat, then that lens won't be enough. You're going to have to add an extra set of lens, maybe contact lenses or glasses, to focus the light onto the back of the retina just right. Now, there in the back of your eye is your retina. And your retina is a membrane that holds all of your rods and all of your cones. Specifically in your retina, in the portion where the light focuses the best, we call that the fovea. So the fovea is just part of the retina. And in your fovea, you have the most concentration of cones. And because there is an abundance of concentration of cones there, then you see color best in that focal point. Um, in your periphery, color is not as perfect. Uh, you clearly have cones in your periphery as well, but not to the same level as in the focus, in the fovea, which is why sometimes you're sure you saw a yellow lab off the corner of your eye, but when you look, it was just a bush. There was nothing yellow or lab looking about it. It's because, again, the amount of color that you can see there is not really as powerful as in your focal point. Now, another important part of your eye is what is sometimes called your blind spot. So, in your retina, you have all of your rods and cones, which are connected to another set of cells, ganglion cells, which they themselves send out axons. And it's those axons that come out through this optic disc and become your optic nerve. If you've ever seen an eye, maybe in a movie or in a YouTube video that has popped out of the socket, well, it's dangling there by your optic nerve. And your optic nerve are the axons of those ganglion cells sending information from the eye to the brain. But there is a problem with this. All of those axons come out the same spot, this optic disc. And so that means that there are no rods and cones in that portion of the eye, which means that your eye does not see anything there. There is a blind spot. Now, if you're looking at the wall or something in front of you, there doesn't seem to be a blind spot. Why? There has to be a blind spot because we know for a fact that uh, there is some missing information. Well, what you have to remember is that your eyes collect visual information, light information, but your eyes don't draw the picture that you're seeing in front of you. Your brain does. And so, what your brain does is that it makes your eyes sort of flicker. You're never really staring deeply, perfectly at something. Your eyes always move ever so slightly. Um, and any information that isn't being sent by the eyes, the brain, well, it just makes it up. It paints it in there. This is why sometimes if you're high on a specific drug or you're just hallucinating for some other reason, you see things that aren't there. Even though your eyes don't see a monster in front of you, your brain paints it in because your brain has the ability to just paint whatever it wants. And if you're high, or sometimes if you're schizophrenic, or sometimes if you're going through a manic episode, your brain just stops taking its cues from the eye and it paints something extra. This sometimes happens to you even though uh, you haven't been doing drugs or anything like that. Sometimes you see a yellow lab off the corner of your eye, and when you look, it's not there because some information was sent from the eyes, and your brain goes, I didn't get that. Well, let me just paint something extra here. Well, the same thing happens there with this optic disc. When this blank information or this hole in your vision um, doesn't send the right information, well, your brain just paints it in. Most of the time, it'll just move your eyes ever so slightly to get that extra piece to make sure that whatever it drew isn't wrong. But if it doesn't get that information, it doesn't matter. Your brain still paints it in. As you're doing your packet, I do have a list here of all of the items that I just talked about, so you can look at it. Remember that this is located in your notes section as well, so you can just open up the PowerPoint. Now, what you're looking at here are your rods and your cones. Um, you'll see that at the very top are your rods and cones. They will collect the light information. Those are passed down to some bipolar and horizontal cells up here. And then eventually all of those cells are going to send the information to your optic, or I should say to your ganglion cells, which will eventually go out to your optic nerve to the brain. And over here in um, the picture, what you're seeing is uh, a microscopic picture or an enhanced picture where you can see the rods and the cones. The rods there are the purple looking ones that look like rods, and the cones are the ones that look more like cones. They're colored in green there. Now, I did mention that some people are colorblind. And a lot of times people think that people who are colorblind see in black and white, but that's not right. Usually, what's happening is that if you're colorblind, your cones are affected. Some people are colorblind because they don't have that specific set of cones. For example, they don't see the color red because the cones for red don't exist in their eye, in their retina. But sometimes they do have the cones for red. It's just that the cones for red aren't very sensitive. And so that's going to affect how they perceive the world. Sometimes, as I mentioned, they lack uh, the ability to see green red. That's this top left corner deuteronomaly. Um, this person probably has a cone that isn't very sensitive. And so they don't see red very well. They are also, in their perception, is also going to affect other colors, purples and oranges. But basically, red is going to be affected. If they're missing red altogether, then that's going to be closer to uh, protanopia, which is going to be the lower left-hand side. Um, and this person, as you can see, there's no red. Not even the browns are visible here. Um, and then, of course, in the lower right-hand side, you're seeing someone who cannot see blue. Um, Again, it could be that they're missing the cones or that the cones aren't very sensitive, but that's going to affect the color um, of blue and everything related to blue, which is going to include purples. Um, Now, in the top left-hand side, you're seeing someone who has normal color vision. You might have heard that dogs and cats are colorblind. And again, people think that dogs and cats only see in black and white, and that's wrong. Dogs and cats have a problem with red. And so they're probably going to see closer to this protanopia version of the world. This is why if you throw a red ball into the green grass, your dog can't really see that, not very well. It's the ball is going to get lost in the grass. Even though to you, the difference between green and red are super big, and you're going to see the red in the green grass very easily, your dog won't. Because your dog won't be able to differentiate the red from the green. And if you look here in this section, it just looks like they're all just green. That's the way your dog would see the difference between red and green if you look at the normal vision. Now, if you were to throw a blue, this doesn't really show a good blue here. If you were to throw a blue ball into the green grass, your dog would see that very well just with their eyes because your dog can tell the difference between blue and green very easily, but not between red and green. Um, Obviously, for rods, uh, your rods would determine the amount of light or brightness versus dimness in the picture that you're seeing. Oops. Um, Again, here's just another version of that with the red apple. Looks like green if you are missing that cone or if your cone isn't very sensitive. And you'll also notice that this very green apple also loses some of its shine. It's not quite as lime green because in missing the red, it also affects how well you see the green. Let me make a quick point between color created by light and color created by pigment. When you're in art class, if you're trying to make black, you're going to take red, blue, and yellow, and you're going to mix them together as perfectly as possible to get that black. Um, and if you're trying to mix orange, then you want to mix yellow and red. If you want to make purple, then you're going to want to mix red and blue. And if you want to make green, then you want to mix yellow and blue. That's because red, yellow, and blue are your primary colors, and orange, green, and purple are going to be your secondary colors. In light, it doesn't work that way. In light, red and blue are still primary, but green is the primary color in light. And if you want to get yellow, then you got to mix red and green. If you want to get purple or magenta, then you got to mix red and blue. And if you want to get a lighter color of blue, um, or yeah, then you're going to mix the green and the blue. In old TVs, if you've ever seen an old TV, they usually have lamps, and you got to control the lamp sometimes. And the lamps are green, red, and blue. And in modern TVs, they, those are still the three main colors. Sometimes they will add a yellow or yellowish lamp to sort of control the color contrast better, but that's just a technology issue, not a color necessarily issue. Now, I told you earlier that to make black with pigment, with paint, you got to mix all the colors. But to make black with light, you have to the light has to be absent. Um, if you're looking at something black in front of you, your black shirt or your black computer, then what's happening is that when the light hits that object is absorbing close to 100% of the light. Not 100%. If it was 100%, you would get weirded out by that. It would look like there's a hole in the world in front of you. Scientists sometimes try to make substances that are perfectly black, um, specifically because that allows for special ways of cooling things. Um, and people who see those objects often say that it's kind of weird and sort of nauseating to look at it because it just kind of looks like there's a hole in the middle of whatever you're looking at, in the middle of space. If you're taking all the lights, green, red, and blue, and you sort of spin them, your eye will detect that as white. When you're looking at the white wall, for example, what's happening is that that white wall or the paint on that white wall is reflecting close to 100% of the light. Not 100%, but close to 100%. So you perceive that as white. People often ask why mirrors do what they do. Mirrors do actually um, reflect back 100% of the light, so that not only the light coming from the light bulb gets reflected, but when that light bulb hits me, I reflect some light out, and that mirror will also reflect the light that I reflect back out. A mirror reflects 100% of the light in 100% of the angles. And so that is why you can see things from a lot of different angles in a mirror. Um, it's uh, any object that does that will reflect an image because it's reflecting the light that you reflect